So our research object is categorized as three. One is advanced of agriculture production systems. Second is reduction of the energy consumption and environmental impacts, and advanced utilization of agricultural information. So one topic, this is the vibration reduction for the agriculture tractors and the combine harvesters by using signal processing approach. And the next one is, today I will show you this part. That's numerical modeling of the soil compaction of the patterns. This is an optimal design of the combine harvester. Threshing part and shaking tables. This is the separation of the grains. So two types of separation method exist. One is the vibration separation. Second one is wind separation fan. So this in this part we use CFD analysis. Okay, so we are going to computational mechanics, the introduction and its application to biosystems engineering. Okay. So as you know, why do these phenomena occur? So the bridge is collapse, or so railway collapse due to the earthquake. So Japan has many kinds of earthquake. So the numerical computation approach is very, very important to establish the highly safety structure. So how to describe this kind of deformation by using computational simulation? So in that case, we have to make a constitutive model to describe such kind of deformation, and by boundary value problem or discretization is important. So crash of cars. So this is very, very good material. Why? So plastic deformation can dissipate the energy to sound and plastic deformation and heat. So in this case, the deformation part 1 and 2 and 3 like small. So the dissipation of the energy is very small. This is half of it. This is very big dissipation of energy. Dissipation is big, so the damage of the body, human body, is reduced. So material design of crafts is very, very important. So in the previous, such kind of evaluation or material design or structure design is due to real test. The price of the testing is very, very expensive. So now some part is go to the simulation. This is construction by using construction machinery. How much soil is covered with previous one? So and how many compactions is done in the one place? So this is controlled by the GPS information. So but soil type and how much compaction is required. So these information should be how can I say, calculate or simulate in the previous stage. So this is also a if the Shinkansen design when the Shinkansen design. So in that case, computer simulation also needed, but in our focus, this part. So log. So the travel or pass number of paths of the Shinkansen, the log mass is gradually compacted. So in that case, shape is a little bit changed. So this is change of shape is due influence for the vibration of the Shinkansen. So we have to control the constant value of the settlement. To establish or to estimate the compaction, so we use numerical simulation. So like this is a ballast, which we call the rock mass of the train. So this is soil compaction. So soil compaction is caused several problems. So the elongation of the root was influenced like that. So penetration ratio decreased. In this case, the plant height is not so high, become not high, and then the crop quality become bad. So sometimes people want to reduce the soil compaction, but we have to control the compaction reality. So computer should make something use. And the breakage of the tubes of chair tubes due to vibration or due to reaction of the forces from the soil. So finally the part of the break like that, bearing part is broken. So we change the material function or material constitutive model. So from the soil or from the metal to biomaterial. So we can consider about what kind of damage occurs the fruits and vegetables due to a vibration of the transportation. So this is also what I think this part is interesting. I want to make the model for fruits, model for tomato, or model for strawberry, model for what? So, if you want to interesting study this part, please come to Kyushu University. I want to start this study. Okay, so we are going to the deformation non-materials. So first of all, I will explain about the one-dimensional case. So it's simple case. So this is a summary of your strength material. So this is one dimension bar. So the size is L0. Both ends pulled by force F. We apply force F. So the bar is deformed like that. Delta L is a deformation or it's a displacement of the end of bar. So it means that deformation is so the displacement bar is delta L is like that. And then F is a pull out force. So if the material is a linear elastic, so and the spring constant or material constant is K, in that case the linear relation is 1 by K. But F is not so good information, or the not good difference value, so I use a stress. Why? By using stress, okay, so this is the question, which is the significant, which is the big force? Oh, not big, which is which damage is bigger? For example, for bar, left hand side or right hand side? Right hand side. So this is a cross-sectional area is small rather than left one. So the stress is more than left one. So we have to define the stress, F divided by air cross-section. So this is the normal stress, definition of normal stress. So this, sorry, so this one, as he said, so this part. So this significant or influence is more than left one. Stress is big, the damage, the influence of the bar is big. Okay, so we are defining the material deformation. The left-hand side is elastic material. We have two elastic materials, linear elastic and non-linear elastic. Both material property are same property, not same. So how can I say? It means that if the apply the force, the material deform, but eliminate the force. So the deformation is completely back to the initial state. So this is elastic. So the stress applied, so the deformation like that, but stress removed, deformation should be recover or back to the initial point. This is meaning of elastic. Sometimes like that. This is not elastic. This is a viscoplast elastic something. Same line, keep a same line, go and back. This is elastic. Not keep the same line, it is viscoelastic. So this is non-linear elastic, going back, going up and back. So right hand material is not elastic, so this is inelastic or non-elastic. So real material have such kind of property. Soil, metal, maybe tomato also. So push the tomato by hand, so it does not recover. So this sometimes when my son was very young, so touch the tomato in the market. So I have to buy. So this is inelastic deformation occur the material. So we have to consider what kind of damage occur inside of the material. So in that case, we have to make a constitutive model, material and stress relation, or so deformation and stress relation. This is very important. So in this blue card, this is the hardening material. So material become hardened due to plastic or inelastic deformation. Sometimes the soil has softening after the peak. So very compacted soil, compressed due to the soil test apparatus, so peak and then going down. So this is a softening. So particle, impact, how can I say, void of the inside soil mass become big. So the stress going down. From this state or from this state, the stress removed, so the property become elastic. Going back. This part is elastic, inelastic, plastic stress. But we have to consider well about what kind of property occur in the material. Sometimes very, very special material exist. For example, shape memory alloy. You know the shape memory. Shape memory. Shape is memory by the deformation like that. But if the material input water, hot water, so all memory is completely eliminated. So that kind of property is quite different from the constitutive elastoplastic constitutive relation, which explain from now. So, what kind of deformation, what kind of behavior occur for the material, so should be considered by how can I say, researcher. You have to test again and again. Or what is deformation? What is a microstructure change? So you have to carefully check. So first of all, we model this type of deformation, but this part is a little bit complicated. So we simplified. I simplified this property, elastic and elastoplastic, or inelastic, to two parts. So this is one of the model. So real behavior has a no smooth property, but model behavior does not have smooth property. It's okay, but this is one of the assumptions. In elastic deformation, we can define the material equation or elastic material constitutive model equation is like described like that. So the sigma equal elastic modulus multiply the epsilon. The epsilon is the increment of the this one, and sigma equal E epsilon. This E is the elastic Young modulus is a constant. In that case, we can immediately integrate from here to there. The two equations is the same meaning. But elastoplastic material, for example, this part. So from here, you can eliminate the stress or remove the stress. So the stress go back linearly from here to there, So if we consider, I want to say, so the eliminate from here to there, for example. Here to there, or someone consider the here to there. So inclination of all curves are same, but if we consider one of the source here, in that case, we have many kind of the solution exist. Well, this is also one of solution. This is second solution. It's also one of solution. This is also one of solution of this curve. So in that case, we cannot define such kind of equation. So sigma and epsilon is one by one. So this definition cannot use in the elastic deformation material. So we use this one. D sigma, this, so we use D sigma and one, okay, so back one. We use this one, upper part of only use this one. CEP is an elastoplastic matrix, or this is a stiffness matrix. So this is actual, not actual, so student can intercept. Every time make a question. Yeah. Oh, this part is not understanding. Please make a question. Okay? This is very, very important. So I want to decompose plastic deformation and elastic deformation in the elastoplastic state. It means that deformation is this one. Is an elastic part and plastic part. d epsilon is divided by elastic and plastic. So this is a first assumption and concept in the elastoplastic theory. So now we apply d epsilon. D epsilon equal, so if d epsilon minus d epsilon p. So this is it's okay. So this is move to the left hand side and move here. So why we want to use a d epsilon? D epsilon is every time fixed. So because E is a constant, for example. In that case, if d epsilon is defined, so stress increment is defined exactly. So this, if this d epsilon is fixed, stress increment is fixed. D epsilon p is very difficult to explain in the first stage. But if we know the elastic deformation, so we can get the stress increment. So d epsilon e multiply e your d sigma. This is so this part. D sigma equal d epsilon multiply e. So this is a stress increment. But in this stage, we don't know this part. We have to define this value from the computation. So we are going to the next. We introduce yield condition. So yield surface. This is a material. If stress reach this surface, the deformation, inelastic deformation start. So this is yield of the material. Yield is a irreversible deformation occur from this surface. Inside of the yield surface is a purely elastic domain. So no elastic plastic deformation occur inside stress. If stress moves like that, no plastic deformation occur. But after stress reach to the yield surface and then move there, so plastic deformation occur. So in this state, surface become big, and then plastic deformation occur due to the expand of the yield surface. This is a hardening process. In this process, we can write by using this equation. This is very easy understandable because left hand side is the shape of the surface, left hand side is the size of the surface. For example, please image a circle. X square plus y square is the shape of the circle. So R square is the shape, size of the circle. So R square is here, X plus y square is here. So if we want to change this, if we want to shift the circle, so x minus 1, for example, x minus a square plus y square. So this is the shape. But we apply such kind of same manner to the yield condition, which we call yield condition.